we are honored to have with us today Alex Iosevich. My theory about Alex is that either he doesn't sleep or he has an identical twin that does some of his work for him, because he seems to be everywhere and do everything. He works in analysis, in combinatorics, in data science. He has an insane number of PhD students, works with undergraduates, has programs in other countries. And if I continue, he won't have time to give his talk today. Yeah, I can be quiet now and let's hear about VC dimension and point configurations. Thank you.
Thank you very much for a very kind introduction, Adam. It's an honor and a pleasure to be here, and it's great to see so many familiar faces. So let's see, I need to share the screen again, I believe. Okay. So what I would like to talk about is distance sets from a point of view of complexity theory, although I'm using those terms somewhat loosely until I make them precise later in the talk. Okay, so one thing is, please interrupt me anytime for any reason. I enjoyed when people are actually listening to my talk as opposed to just going through slides. Okay, let's go. Okay, so the talk is dedicated to memory of Jean Bourgain, because one thing that occurred to me as I was writing the slides is how much he influenced every page. Okay. And okay, so here's a general overview about how I think about these types of problems. So there are many problems in mathematics that can be described in very broad strokes from the following point of view. You have a function from a suitably large space to another space, and this function is suitably non-trivial. Okay, then the image is large. It may be that every problem in mathematics can be phrased this way, but one just very simple example from our undergraduate days is Picard's theorem, that if you have a function from C to C, which is entire non-constants, then the set of values that f of z assumes is either the whole complex plane or the plane minus a single point. And of course, one can talk for days about these types of examples. And in this lecture, I'm going to focus on a particular class of problems of this type that revolve around point configurations. Okay, so what is a distance set? You take a finite subset of Rd, you define a Euclidean distance. One of many things I will not have time to talk about in detail is what happens if you change the notion of a distance. Okay, and you count how many distances does this finite set determine. Okay, now it's pretty clear that the total number of distances is n choose 2. Okay, it's not pretty clear, it's very clear. However, these distances may repeat. And this is, so this area is called extremal combinatorics, or as was put to me once, man bites dog combinatorics. We're not looking for a generic example. We are looking for an extreme example. So what is the smallest possible number of distances determined by a set of size n? Okay, and this is known as the Erdős distance problem, which, as far as I know, was formulated in 1945, though I seriously doubt it. That's when the first result was published. For all I know, Erdős had this idea 10 years earlier. Okay, so let me go straight to the critical example. Now, is this a critical example? We don't know, but we believe this is a critical example. So you take the piece of the integer lattice containing n points in a cube, okay? And so the size of the distance set is just the number of values of the quadratic form, x1 squared up to xd squared. And this is a classical problem in number theory. Elementary circle method can be applied to this. But if one wants to get a basic idea of what's going on, one doesn't need any advanced number theory, because the values of this quadratic form are simply integers between 0 and dn to the 2 over d. Therefore, you can't possibly have more than a constant multiple of n to the 2 over d values. Okay, so what this says is that in general, we cannot expect n points in d-dimensional space, d bigger than or equal to 2. The one-dimensional case is silly. We cannot expect that set to determine more than n to the power of 2 over d points up to constants and logarithms, because as we know in dimension 2, the number of values this quadratic form takes on is actually n divided by square root of log n. Okay, because of what is to me perhaps one of the most beautiful facts in elementary mathematics, that you can't write a positive proportion of all the integers as a sum of 2 squares. This is when I realized that mathematics was a beautiful subject. All right, so Erdős conjectured indeed that if the size of E is equal to n, then the number of distances is bounded below by n to the 2 over d. So 1 squiggle means that I can compute constants, and indeed I can't. And 2 squiggles means that I'm varying all the logarithms also. Okay, so this is the Cherry-Tau notation. And we just saw where the exponent 2 over d comes from. So this is a picture of Paul Erdős shamelessly lifted off the internet without attribution. Oh, this is being recorded and might go to the FBI. Oh, well, okay. Okay, so after more than 60 years of efforts by many outstanding mathematicians, the Erdős distance conjecture was finally solved by Guth and Katz in 2011 using a combination of group actions, polynomial partitioning, and incidence theory ideas. By the way, I should mention in passing that that theory of this type is exposed very, very nicely in Adam's book, and I recommend it very highly. Okay, and
you are too kind. You're too kind. That's all.
It's just true. And in higher dimensions, the best known result, which is roughly 2 over d minus big O of 1 over d cubed, is due to Shoimoshi and Wu. But the conjecture is still open in higher dimensions. You know, since this is largely an expository talk, I cannot resist a very quick story about how I found out that that Guth and Katz proved their conjecture. I received a text message from Nats Katz when I was in the Buffalo airport, and I started jumping up and down and yelling, "They did it, they did it, they fill in the blank did it." And a policeman walked up to me and asked me if everything was all right. And in a rare moment of good judgment, I realized that if I tell him what's going on, he will arrest me. So instead, I just said, yes, everything is fine. I'm going to sit down now. And he was like, you do that. All right. So now, having introduced distance sets and conjectures and roughly what is known, what I would like to spend a few minutes on is why should we care about distance sets? This is, again, a subject on which numerous lectures can be given. I just want to give you one example, which is particularly near and dear to my heart, because this is how I stumbled into combinatorics many years ago. Okay, so let's take a bounded domain in RD. And one of the fundamental questions in whatever you want to call it, Fourier analysis, functional analysis, is whether L2 of this domain possesses an orthogonal basis of exponentials, otherwise known as Fourier basis. So for example, we've learned at an early age that the answer is yes if omega is a cube. This is just standard Fourier series. But if omega is the unit ball in dimensions 2 and higher, the answer is no. And this is where distance sets come in, as you will see in a moment. Okay. So this is a result due to Nats Katz, Peterson, and myself proving that L2 of the ball does not possess an orthogonal basis of exponentials. This answered a question posed by Ben Pugletti, I'm butchering his name, but I can't pronounce Danish names, in 1974. And it's also kind of to me, a very instructive example. The reason the problem was open for so long is because it's not an analysis problem at all, as I'm hoping to convince you momentarily. Okay, so what does it mean that we have an orthonormal basis? Well, in particular, it is very easy to deduce that the spectrum, so you have basis of the form e to the 2 pi I x dot lambda, and it's very easy to see that different lambdas are separated. Okay, this is roughly on the level of second year analysis, undergraduate analysis. Also, it is not that difficult to show that lambda has density equal to the volume of the ball. Okay, so it has positive density, so these points are everywhere. This is a classical Berling density theorem, which is a beautiful result, but we don't need it for what I'm about to show you, because we just need to know that the density is positive. Okay, and what does orthogonality mean? Orthogonality means that the Fourier transform of the indicator function of the ball is 0 on the difference of any two elements of the putative spectrum. And the Fourier transform of the indicator function of a ball is given here in the explicit form. And what it tells us is that a distance between any two elements of the putative spectrum is a 0 of the Bessel function of order d over 2. Okay? Now, the theory of Bessel functions is extremely well developed, but we don't need to know much about it at all, except that we just need to know that these zeros are uniformly separated, which is a calculus 1 exercise. Okay? And so in particular, what we know is that if this spectrum exists, if you look at the elements of the spectrum in a large cube of radius r, there are approximately r to the d points of this putative spectrum. On the other hand, the number of distances determined by the elements in this large cube cannot possibly exceed a constant times r, because the distances are all zeros of the Bessel function. The diagonal of the cube has length approximately r, and all of these zeros are separated. So if we are to believe that L2 of the ball has an orthogonal basis of exponentials, this will lead to extremely magical point set, which has r to the d points, and the number of distinct distances is bounded by a constant times r. And based on our discussion about what is known about the Erdős distance problem, this is simply impossible. Okay? There are many variations on this that I'm not going to discuss today, but this is an illustration of how distance sets arise in what one might think is a fairly improbable setting, namely the setting of grungy hardcore functional analysis. Okay? And so let me now go back to distance sets. So there is a continuous version of the Erdős distance problem known as the Falconer distance problem, which to the best of my knowledge was formulated in the early to mid 1980s. In fact, I know it was, I discussed this with you. So the distance set is defined in exactly the same way. And I mentioned that I will not have time to talk about what happens with different distances, but I need to say something, at least in passing, just to illustrate how beautiful this whole set of problems is. And this is a point that was made to me a long time ago by Nets Katz. Suppose that you replace the usual little L2 distance, the Euclidean distance, by an LD distance in dimension d. Then if you want to carry out this type of analysis, even on an integer lattice, you run straight up against the following innocent-looking problem. Is it true that you can write a positive proportion of positive integers as a sum of d/dth powers? For example, can you write a positive proportion of positive integers as a sum of 3 cubes? And as my friend Trevor Woolley puts it, this problem is very unsolved, not just unsolved. Very unsolved means that it's unsolved and nobody has any fill-in-the-blank idea of where to even begin. Okay, so this is again an illustration of a situation in this problem where if you dig in any direction, you very quickly run into extremely difficult questions that are extremely trivial to state. Okay. All right, so the question in the continuous setting is how large does the Hausdorff dimension need to be to ensure that the Lebesgue measure of the distance set is positive? Okay, and this might remind you of a question that keeps popping up on on preliminary exams because nobody wants to spend too much time writing them, namely that if E has positive Lebesgue measure, then E minus E contains an open ball. This is the Steinhaus problem. So the idea here is what happens if this set is much smaller? We don't insist that a different set contain a ball, but we want the distance set to have positive Lebesgue measure. And this provides another connection between distance set theory and sort of hardcore analysis. All right, so what happens in the continuous case in terms of the integer example? This integer example is something that I go back to at least once a week for inspiration. So you take the integer lattice, you scale it down, and you take a q to the minus d over s neighborhood. So what we're trying to do here is to imitate a set of a given fractal dimension. And there's a basic theorem that says that if you take a sparse sequence of such sets, so what I'll show you a picture in a moment, you should be visualizing a union of small balls, okay? Then if you take an infinite intersection of these, you get a set of a Hausdorff dimension S as required. And at any stage Q, you should think of this as a kind of a stage of a Cantor set. You can view this as a Cantor type set. And then what is the Lebesgue measure of the distance set? Well, the distance set involves two types of interactions. Close interactions inside each ball. So that's how you get an interval of length qi to the minus d over s, and large scale interactions. And these are just measured by distances in the integer lattice, okay? And we've already discussed what happens here, that the number of these distances is bounded by a constant multiple of qi squared. So if you put everything together, what you see is that the Lebesgue measure of the distance set goes to 0 in general if s is less than d over 2. Moreover, this reasoning comes from the exactly same lattice example as the discrete problem. So this d over 2 exponent in the Falconer problem has the same origins as the 2 over d exponent in the Erdős problem, which suggests very strongly that the two problems are linked. And this is another beautiful subject matter that I won't have time to discuss, but if anybody is interested, let me know. Okay. All right, so this is the picture. We scale down the integer lattice after limiting it. We thicken it by q to the minus d over s, and then we count the resulting distance set. So one way of thinking about the Falconer problem on a sort of a discretized level is now, instead of counting distances between discrete points, you're counting separated distances between discrete points. This is an oversimplification. I want to put this in neon lights, but it does reflect many of the salient features of the problem. Okay. All right. So this is a conjecture, 1986. So based on which flows out of what we just discussed, that if you have a set which is compact of Hausdorff dimension bigger than d over 2, then the Lebesgue measure of the distance set is positive. And this is a picture of Kenneth Falconer, also shamelessly lifted off the internet. Also, please don't tell Kenneth, but he doesn't look like that anymore. Okay, let's go. So just a quick timeline to get an idea across of how much people are suffering over this problem. Okay, so the exponent d plus 1 over 2 was obtained by Falconer in 1986. It was improved by Bourgain to 13/9 in the plane, but as always, Bourgain did much more than improve the exponents. He laid down the method, which is the basis of everything that was done, that has been done since then on the problem. Then Wolf sharpened the exponent to 4/3, and Erdős obtained d over 2 plus 1/3 in higher dimensions. So notice that it took 20 years and much of the machinery of modern harmonic analysis to go from d plus 1 over 2 to d over 2 plus 1/3. Okay, so this is a superficial indication that maybe the problem is not trivial. There was a long period of inactivity until there was a paper by Du, Guth, Wu, Wang, Wilson, and Zheng, who got exponent 9/5 in R3 using decoupling. This is a beautiful theory that was very significantly developed over the past decade by Bourgain and Demeter and Guth and other people. Then Du and Zhang obtained d squared over 2d minus 1, which is roughly d over 2 plus a quarter, a little worse, using decoupling and Schrodinger methods. And so Guth, Wu, Wang, and myself dropped the exponent 4/3 to 5/4 in R2 using decoupling and a pruning procedure. Okay, so this is a rough overview of this problem. And there is a problem that runs in parallel, which I really, really enjoy. And this is the finite field version of the problem, which was invented by Tom Wolfe in the 80s as a kind of a playground for harmonic analysis techniques in a less technical setting. It turns out, however, that one needs to be very careful in treating finite fields as a playground for Euclidean space because arithmetic considerations matter, and I'm going to point this out in a moment. So here, the so-called distance is just the sum of squares. It's the element of the field. Taking square roots in finite field can be bad for your health. And in analogy with the classical Erdős problems, one can ask how small the distance set can be. This turns out to be a difficult version of that problem, although there are some wonderful results in that direction by Bourgain, Katz-Kanyagin, Rudnev, Tao, and others. But the reason this is a difficult formulation is due to the following innocent-looking example. Take Q to be a prime congruent to 1 mod 4. Then, as we learned in algebra, square root of -1 is in the field. And you can take the set TIT, where I is the square root of -1. And notice that the size of this set is equal to P, but the distance set is just 0, because the distance between any 2 points here, let's say TIT and SIS, is T minus S squared plus IT minus IS quantity squared, which is identically 0. Okay? So this says two things. One is this, that, algebra considerations must be respected, and the problem needs to be reformulated in order to be studied in the same way.
I want to complain and give you a hard time for no reason.
Please.
But on the other hand, the same issue exists over the complex, and the problem is still more or less solved over the complex. So there's still something else that distinguishes it.
Oh, no doubt. I'm not saying that this makes it impossible. All I'm pointing out is that you need to reformulate the problem. You can no longer say that a set of size n has this many distances. You need to say something. But I mean, absolutely. This is not, this is not death, just an inconvenience. Yeah. And okay, so here's a theorem. This is joint work with Misha Rudnev from 2007. Suppose that the size of E is bigger than 4q to the power of d plus 1 over 2. Then the distance set is the whole field. Okay. And there's an example that Misha and I constructed together with Derek Hart and Du Co in 2009, which shows that in odd dimensions, this exponent is best possible, even if we only want a positive proportion of the distances. This is due to the existence of a grotesque object in vector spaces over finite fields, namely a sphere of radius 0. Atrocities like this don't exist in Euclidean space. This is why you see better exponents there. Okay, which raises a question in view of what Adam said of what happens in complex space, which I, to be honest, have not looked at, and I'm glad you brought this up because now I will. Okay, so in even dimensions, the only improvement is in dimension 2, the only known improvement, and this is joint work with Chapman, Erdogan, Hart, and Co. in 2012. In the case Q is prime, and Bennett, Hart, Pakyanathan, and Rudnev in 2017. Rudnev and several co-authors lowered the exponent to 5/4 in the case when Q is prime. This is a very beautiful paper from about 2 years ago. Okay. Let me just give you a very quick and very superficial illustration about how the finite field techniques, not the problem that I've already discussed, are different in a finite field and Euclidean setting. So the quantity that comes up over and over is the Fourier transform of the measure on the sphere. Okay, and proving pointwise bounds for this Fourier transform in view of radiality really hardly rises above first-year calculus, and this is really not an exaggeration. Okay. On the other hand, as Misha and I discovered when we started working on the finite field version, if you look at the Fourier transform of the indicator of a sphere in finite fields, to prove the sharp estimate, you run into this innocent-looking sum, which turns out to be the Kloosterman sum. And the bounds on the Kloosterman sum obtained by Veo and Salih in the middle of the 20th century are truly among the more notable results of 20th century mathematics. So it's another indication that one must be respectful of a discrete setting. Things can arise that may superficially seem easy, but are really, really, really quite deep. Okay. All right. So now this brings us to the notion of complexity, which I am at first going to use extremely loosely, and then I'm going to introduce a precise definition. So one way to view the Falconer distance problem in RD or in FQD in terms of complexity is that what we are showing is that if the set is of sufficiently large size or of sufficiently large Hausdorff dimension, which is also a measure of size, then in the sense of distances, it is just as complex as the whole space, in the sense that we are able to recover a positive proportion of all distances. If you allow me to say that positive Lebesgue measure worth of distances is a positive proportion. Okay. And at some point, it sort of started occurring to me that that since this notion of complexity leads to interesting mathematics, what would happen if one brought in more sophisticated notion of complexity? And indeed, as I'm hoping to convince you over the remainder of this talk, it does lead to some rather interesting notions. Okay. All right. So now learning theory comes in, and the Vapnik-Chervonenkis dimension. So just truth in advertising. What really happened is not quite what I just described. It's not that I was just sitting there in a chair one day and thinking that it would be nice to look at deeper notion of complexity. No, there's much more serendipity. I was running a summer program on machine learning, okay? And figured that we should discuss some theory also. So there was a crash course on this wonderful book by Ben David and Charlotte Schwartz, The Fundamentals of Machine Learning. And in this book, there was this Vapnik-Chervonenkis dimension and the basic theory of it. And then one day, Emmett Wyman and I were just drinking coffee, and we said, why don't we just look into this? I mean, what is the worst thing that can happen to us? So some basic definitions. X is a set. H is a collection of functions from a set to 0, 1. And we say that H shatters a finite set C in X if the restriction of H to C yields every possible function from C to 0, 1. Okay, so those of you who've looked into machine learning before understand the significance of this already, but let me just say in passing that the basic idea is the following. If let's say that you want to classify object, let's say cat, not a cat, okay? And you have a bunch of classifiers that you want to use, and you have some reason to believe that that one of them is the correct classifier, say. Then how do you know that you can follow some reasonable procedure and find a good classifier? Okay, well, you take some sample and you take all your classifiers from a bag and you dump it onto that sample. Well, if you keep getting every possible sequence of ones and zeros, you're not learning much. And this is the idea behind Vapnik-Chervonenkis dimension. So first of all, what is the dimension? We say that a non-negative integer n is the VC dimension if there exists a set that is shattered and no subset of larger size is shattered. So beyond that point, you start getting useful information. Okay, and I need a couple of quick definitions. So given a set X, a probability distribution D, and a labeling function F, H is the hypothesis. In other words, H maps X to 0, 1. This is one of your candidates. Then you define the discrepancy as the probability that your hypothesis function doesn't match the correct labeling function. Okay. And here is the notion, which the name I find hilarious. It's probably approximately correct. To a pure mathematician, this just sounds a little disturbing, but then you get used to it. So, because the definition is indeed precise. A hypothesis class is probably approximately correct learnable if there exists a function from 0, 1 squared to n, and the learning algorithm was the following property. For every epsilon and delta, and for every probability distribution, and for every labeling function, if the realizability assumption holds, meaning that in your bag you have the correct labeling function, then when running the learning algorithm on this many samples, identically generated samples, by D and labeled by F, the algorithm returns a hypothesis H such that with probability 1 minus delta, the error is less than epsilon. So probably approximately correct means you can find the classifier which is correct with probability 1 minus delta and error less than epsilon. And obviously any quantitative estimate blows up as epsilon and delta tend to 0. Okay, so the following is a quantitative version of the fundamental theorem of machine learning, and it provides a link between VC dimension and learnability. Okay, so this is a result in, I think that this is a sort of a slight refinement of the result that was proved by Vapnik and Chervonenkis in 1970. I got a hold of the original paper, but it's not easy for me to read because I never learned Russian mathematical terminology. So anyway, theorem, let H be a collection of hypotheses in a set X, then H has a finite VC dimension if and only if H is PAC learnable. Okay, so in other words, if the Vapnik-Chervonenkis dimension is finite, then you can find the classifier that does the job. Moreover, if the VC dimension of H is n, then H is PAC learnable. And remember that sampling size. This is how much you need to sample to run your algorithm. It is bounded above and below by very natural quantities that grow with the VC dimension. They grow as epsilon goes to 0, as they should, because that's when you're making error smaller and smaller. And they also grow if you take delta to 0, as it should, because then you're trying to eliminate the probability of a bad outcome completely. Okay, so this gives you a very quick overview of learning theory in this context. And now let me describe what this leads to when one dumps this theory in the context of finite point configurations. Okay, and let's see, according to me, I have 13 minutes, right?
We're flexible. You can have more.
Okay. Oh, Justin, I was trained by my PhD advisor, and this has now been 30 years. But Chris Salk told me over and over that a talk doesn't have to be good. That's optional, but you have to finish on time.
Our system is having the end time very vague and unclear. So
okay,
it'll be fine.
Very cool, very cool. Then I'll relax and slow down slightly. All right, so you take E to be subset of RD or FQD, okay? And HTD of E is the collection of indicator functions of spheres of radius T centered at points of E, okay? So before I go to this picture, so what is the idea? What are we classifying here? You can view this as a kind of a game. So I don't know, some mythical creature, the devil, say, knows where a sphere of radius 1, say, lives, right? So the devil knows where the sphere is centered, but you don't. But you get to ask the devil questions. And how do you ask the devil questions? You say, is this point on the sphere? Is this point in the sphere? And the devil cannot lie in this particular exercise. Okay? And the learning task here is to find the sphere, at least with high probability and a small error. Okay? And I just want to make sure that I don't oversell this. I'm not saying that this point of view is of practical importance here. Okay? If one wanted to actually identify a sphere in this way in a practical problem, this is not how you would go about it. But it does lead to some intriguing mathematics, as I hope to convince you. Okay. All right. So this is the picture that emerges. So let me explain what this picture is. So you have this set, and now I'm not being specific whether we're in Euclidean setting or finite field setting, because it doesn't matter, except that in finite fields, this picture is fraudulent because of modular arithmetic. Okay. So you're trying to shatter points x1 and x2 and x3. So what does that mean? It means that first you need to find a point. So here it's labeled as y1, 2, 3. That's distance 1 from all of them. That corresponds to the sequence 1, 1, 1. Okay. Then you need to find a point y1, 2, a distance 1 from x1 and x2, but not distance 1 from x3. This is a point y1, 2. And similarly with points y1, 3, y2, 3, y1, y2, and y3. So what am I telling you? What I'm telling you is that in order to show that a particular set or a set of a particular size, a class of sets, okay, leads to a VC dimension, let's say equaling to 3. What this amounts to is showing that any such set must support a point configuration described in this picture. Okay, and there's sort of a very interesting lesson here that this, again, is a ubiquitous theme in mathematics. There is a plethora of results, some involving me, some not involving me, about showing that big enough set contains a particular geometric configuration. However, what we quickly discovered is that in order to prove these VC dimension results, we needed to prove the existence of configurations that was well beyond what was contained in those previous theorems. And this is just obvious. Necessity is a mother of invention. You know, sure, we tried to prove the existence of the most sophisticated possible configurations, but when you don't know what to aim for, it's hard. Whereas VC dimension precisely frames what one should be aiming for, and loosely speaking, it points to the most sophisticated possible configurations you can hope to build in a set of a given size. Because if you could build a more sophisticated configuration, then it would lead to higher VC dimension, which we often know is not true from the constraints of the problem or from dimensional constraints. Okay, right, so this is the picture. And here is a sample result. And this is joint work with Davy Fitzpatrick, Brian McDonald, and Emmett Wyman. This is also an interesting story. So Davy was an undergraduate student in mathematics, then he sort of vanished from mathematics, but he reappeared just briefly enough to help us with this result. Adam, I believe he was in one of your programs, if I remember correctly.
Yeah, I worked on a paper with him also.
Oh, that's right.
I'm curious to hear how he's doing, but I guess later.
Yeah, absolutely, absolutely. So this is the result. So E is a subset of FQ2. It's a two-dimensional vector space over the field with Q bigger than 2 elements. Didn't need to say Q bigger than 2. 2 is not a prime. People who suggest otherwise are wrong. Such that the size of E is bigger than a fixed constant times Q to the power of 15/8. The only thing I want you to notice about 15/8 is that it's smaller than 2. I'm making no claims as to the sharpness of this exponent because I have no idea. Okay, now once again, we take HT2 of E with t not equal to 0. So this is a set of indicator functions of circles centered at the points of the set. Then the VC dimension of HT2 of E is equal to the VC dimension of HT2 of the whole space, which is 3. So once again, I think of it as sets that are sufficiently large being as complex as the whole vector space with respect to this property, which is the VC dimension of the set of indicator functions of circles centered at the points of this set. Okay, and right. So as I said, this amounts to producing the configuration that we discussed. And at the end of the talk, I'll give you just a tiny bit of a flavor for how one goes about these things. Okay. A quick point. Suppose that one wants to do this in Euclidean space, then one quickly runs into trouble. So there's a theorem due to it's either Maga or Maga. I'm not good at Hungarian names either. It says that there exists a compact set of Hausdorff dimension D in Rd, D bigger than or equal to 2, which does not contain vertices of any parallelogram. It's a really beautiful construction, which requires having multiple scales. So there's no hope of building such a construction in finite fields. And indeed, this is not true. Okay. And in particular, if E is an R2 of Hausdorff dimension 2, then the VC dimension of HT2 of E is equal to 2. And this follows from the following result due to Mike Bennett, Crystal Taylor, and myself. And the result says that if you have a set of Hausdorff dimension bigger than D plus 1 over 2, then there's an interval, so that if you choose any value from that interval, it's a positive real number, then you can find k plus 1 points in your set that give you a chain where the side length is t. So the consecutive distances are equal to t. Okay. There are some very interesting quantitative issues that arise when k goes to infinity, but this is again beyond the scope of this talk. Okay, and here let me just put these two pictures next to one another. The first picture you've already seen. This is the configuration that one needs to be able to build in order to prove that the VC dimension is 3. And this is a nasty configuration. I think that that's fair assessment. In order to prove that the VC dimension is 2, it is enough to build this second configuration, right? So we're trying to shatter x1 and x2. So y12 is the fixed distance from both of these. Then y1 is a distance t from x1, y2 is a distance t from x2, and the dotted line indicates that those distances cannot equal to that number t. So this is a much simpler configuration to build, but even that requires a considerable amount of work. Okay, and so this is very much work in progress, but here's a sample theorem. And this is a joint work with Alex McDonald and Brian McDonald. Yes, they are related. They are brothers, and they are both my, so Alex was my PhD student. Brian is my PhD student graduating this year. They also look alike, which, can be hilarious. Okay, so if E is a compact subset of R3 of Hausdorff dimension bigger than 5/2, again, what I want you to notice is that 5/2 is less than 3. Then there exists a non-empty interval I such that for any t in I, the VC dimension of HT3 of E is bigger than or equal to 3. From geometric configurations, it could be as big as 4. And our current methods certainly don't stretch this far. I personally suspect that there's a counterexample for 4, but this is very much work in progress. There are lots of nasty examples in this area of mathematics. Okay, and so let me give you a quick overview on how to prove the VC result in FQ2. Namely, that if the size of the set is bigger than constant Q to the 15/8, then you get Vapnik-Chervonenkis dimension 2. So the key object is a rhombus, which happens to be a parallelogram, in 2 dimensions. So this is why this cannot be done in Euclidean space. So what I want to focus on is how we get around these issues in finite fields, because this will also give you a flavor of things you can do in finite fields that you cannot do in Euclidean space. Okay, so by a result that Misha Rudnev and I proved, if you look at the number of pairs separated by distance t, it is equal to the size of E squared over Q, that's statistically correct, plus an error. And this error ceases to be significant when the size of E runs away from Q to the power of 3/2. Okay, so you can view this as a uniform distribution result because indeed that's what it is. Okay, and so what happens if the size of E is bigger than a constant Q to the power of 7/4? Why 7/4? You'll see in a moment. Okay, then if you look at the pairs separated by distance t, all pointing in, okay, so one second, what am I saying here? Oh, yes, no, then just the number of points separated by distance t is bounded from below by a constant Q to the 5/2. I simply squared Q to the 7/4 and divided by Q. Just that when I have to do arithmetic, everybody needs to hide and run. So it follows just by the pigeonhole principle that there is a non-zero direction. So that if you look at pairs, so that x minus y is v, and the length of v is fixed to be that t, then the number of such pairs is at least a constant Q to the 3/2. Okay, so why am I telling you this? So sorry, I forgot to draw the picture. You should visualize a bunch of pairs separated by distance t, all parallel to one another. Okay, and then you use the following silly trick. Consider the set of x's from these pairs, right? And note that my result was Rudnev implies that if this constant is large enough, then every possible pairwise distance is realized among the elements of this set, right? So just visualize a bunch of parallel segments separated by distance t. But then there must exist a situation where if you draw the lines, completing them into a quadrilateral, that distance is also equal to t, and that means that you have a rhombus. Okay, so what this does is it produces a rhombus of side length t, but moreover, if one does this analysis carefully, it produces many rhombi of size t. And then just to take you back to the picture, this is this picture over here. Notice that rhombi, sorry, it's a Latin word, so it's rhombi. Rhombi are at the heart of this picture, right? Because you have a series of 3 overlapping rhombi. It turns out that technically the most difficult part is producing lots of these rhombi. The remaining part, where you string them together, is messy, technically complicated, but ultimately quite doable. And I think that I'll stop here.